Okay, so we're going to start waves today. Waves is the last major topic in Physics 20. Okay, so before Christmas, we're going to go over properties of waves, we're going to go over wave behavior, and universal wave equation. If we're lucky, we might get into interference, okay, before next Thursday. And then when we come back, we're going to do standing waves and Doppler effect, unit exam, final exam, done. Speaking of final exam schedule came out yesterday. Your final exam is going to be January 26th at 9 a.m. I don't remember what room it's in, but I'll get that information for you. It's not in here is all I remember. I think it's down in math wingers. Anyway, I'll figure it out and I'll get it up on the board for you there, but that's the date, okay? So make sure you don't have anything else going on that day, okay? Because you kind of need to be here for your final exam. We generally frown on people not writing it at different times, because, yeah, that's not good. So make sure you're ready to go for January 26th at 9 a.m. Usual final exam stuff will apply. Be here at 8:45. We'll open the door. We'll let you in. Okay. You can't have your phone in here. We're going to clear your calculator. That's another big one. Okay. So if for some reason you've been using your graphing calculator to store vital information, know that that will be cleared prior to the exam. Okay. And you will get a fresh formula sheet for the final exam, so don't bring yours, okay? Bring some water or something to drink, maybe a nice exam appropriate snack, okay? And by exam appropriate snack, I mean like a granola bar or a banana or something quiet and not smelly. No, don't be like the guy that we had brought in the 500-gram bag of Doritos, okay? And people were going to kill him. Okay, because he not only was crinkle the whole test, but he would chew with his mouth open. Yeah, so it was all bad. Okay, and I've seen it all. When it comes to what food, I saw a guy bring in a full-on meal. Okay, he went to the grocery store and he had a cooked chicken, and he had some potato wedges and some gravy and some vegetables and a dessert. And he brought that all into the gym. The whole gym smelled like cooked chicken. Which, I didn't mind. I don't like the smell of cooked chicken. But not everybody does, and it would be pretty distracting if you didn't, or if you were hungry and you can smell somebody else's really awesome food, okay? It's inconsiderate. It was funny, but it was inconsiderate, okay? So, yeah, don't do something like that. How you can have people, they'll bring in an orange, right? Thinking, oh, I brought myself a nice healthy snack, and they start peeling it and the whole room smells like orange, which not everybody likes, okay? And when they're all done, their fingers are all sticky. And then they gotta go wash their hands, and so, bring something that's not gonna get your fingers all sticky, not gonna stink up the room, and not gonna bother others, okay? It's not like you need to bring that much food, okay? It's only a 2-hour test, and you're not gonna be in here all day or anything like that. Okay? And of course, if you usually write elsewhere or have accommodations for your exams, those will still apply, and you will write in learning support and all that good stuff. Okay? Yeah, so just make sure that you're ready to go for all of that, okay, for January the 26th. You guys are the last exam, okay? So I don't know when I'm going to be available for help yet during exam week. We just got the supervision schedule, so I have to have a look at it and see when I'll be available and when my room is actually available. Okay? There may not be a lot of opportunities during exam week for you to come in and see me for help, but I will figure out when they are and where they are and put them on the board when we get back from Christmas. Okay? All right, questions for the final? All right, so for today, properties of waves. Okay, we're going to learn the characteristics of the two kinds of waves. The two kinds of waves are transverse and longitudinal. Okay, not longitudinal, that's lines on a map. Longitudinal is a type of wave, so it's not spelled incorrectly. Okay, it's a type of wave, not lines on a map. Okay, we need to understand how waves are created and how they're propagated. Okay, so that is how they travel from one place to another. Okay, and finally, we need to understand the properties of waves A lot of those are going to be familiar: period, frequency, amplitude, okay, things like that. Those properties of simple harmonic motion will carry over to waves, but there's also a few properties of waves that are not present when we're talking about simple harmonic motion. That would be things like wavelength, speed, okay, things like that, because waves obviously travel from place to place. Okay, so what is a wave? Well, it has a frequency, or waves have a frequency, but what is it? Okay, water waves are an example, okay, but how do we get them?
Isn't it like a disruption of like a certain, like, because there's sound waves, but there's also
Like water waves, sound
Yeah,
waves, light waves,
I can't think of like the word I'm looking for.
medium?
Sure.
Okay, that's the word she was looking for, because waves are a traveling disturbance, okay, or disruption. Something has disturbed a medium. Waves require a medium in which to travel, light being an exception. Light waves, because they're their own particle, can travel through the vacuum of space, okay? But all other waves require some form of matter, a medium, in which to travel and propagate. They have to have something to disrupt and carry their energy, okay? Because waves are energy. They're not matter. They disrupt matter, they travel through matter, but waves in and of themselves are not matter. They carry energy from one place to another. So we can make waves, but we make waves by doing work and transferring energy to a medium, in which the medium then carries it away. Does that sort of make sense? So it's kind of difficult to quantify waves for a very long time, because we would often get confused between the wave and the medium in which it was traveling. Okay? That's why we have the expression in space, no one can hear you scream, because there's no medium in space to propagate the sound. Okay? Right now, you hear me because my vocal cords are vibrating back and forth and disrupting the air, and the waves are traveling outwards from there. Okay? If I clap my hands, okay, I force the air out from between my hands, that causes a disruption, and the sound travels outwards through the air. Okay? Does that make sense? Okay? So a wave is a traveling disturbance that carries the energy of that disturbance away from the point of disturbance. Okay. All right, so a wave is a traveling disturbance, and they require a medium in which to propagate. Water, air, wood, concrete, the Earth's crust, okay? Anything that is matter has the ability to transmit waves. Not all things transmit waves equally, okay? And not all things transmit both kinds of waves equally. Okay? In fact, some media transfer longitudinal waves exceptionally well, and other media, and those same media do not transmit transverse waves at all. Okay? As an example, sound travels very easily through solids, but it actually doesn't propagate very well through air. Okay? While water waves, okay, they travel very easily. They're transverse, okay, through things like air or water, obviously, okay, but they can also move into air, okay, but they travel very poorly through a solid. I mean, did you ever see a door go, right? Like, you can't like grab onto a door and do like this, like you would with a blanket or a spring, and have the wave travel through the door, okay? It's rigid, it doesn't work that way, okay? But a door transfers sound way better than air does. Okay, or way better than other materials would, because in a longitudinal wave like sound, the particles oscillate back and forth like this, okay, as opposed to up and down. Okay, so it's more about contact than it is about up and down movement. Okay, that's what we're going to see as we go along here. Okay, so if the motorboat in this picture, okay, disrupts the water, so as it moves through, it pushes the water down. And after it's passed through, the water, because it's elastic, comes back up. Okay? And you've seen this. If you've ever seen, like, you've thrown a rock into water, okay? The water goes down, okay? You sometimes see the little splash come up, and then you see the ripples traveling outwards from the point where the rock went in. Okay? Well, it's the same here. We push the water down, we disturb it, okay? And the water bounces back up, and it oscillates up and down a little bit with simple harmonic motion, which creates a series of waves. Okay? It's because water can oscillate like that that we see more than one wave. Okay? The rock only disturbs the water once. Okay? It doesn't like jump into the water, jump back out, and keep going. Okay? But because the water has elastic properties, right? It's a polar molecule. Okay? It's going to oscillate up and down and create a whole bunch of waves that will travel outwards. Okay? Same with this boat. Now, the reason we know that these waves carry the energy of this boat's disruption is because when they get to the fisherman who's here in this boat, what happens to his boat? Right, bobs up and down, right? Well, if you're going to lift up the boat, does that require energy?
Yes.
Okay, well, the waves are carrying the energy of the motorboat to his boat, and then they can do work. Okay, obviously waves can do work. We use tides and things like that for generating energy in some places. Okay, so waves can carry energy from one place to another. Okay, that's what we have to understand. So a wave is a traveling disturbance. It needs a medium in which to propagate. It's got to have some matter that it can move. Okay, otherwise it can't travel from A to B. Okay, now here's the other thing that confuses people about waves. When a wave travels from here to there, does the water travel from there to there? No. What's the water doing? Exactly. The water oscillates. It just goes up and down. It was disturbed up and down. That doesn't make the water go outwards. Okay? A wave in a lake is not like a flowing river. Okay? In a flowing river, water goes from A to B. But when a wave moves, the water just goes up and down. If it didn't, and I threw a rock in the middle of the lake, there'd eventually be a hole in the middle of the lake. Okay? Because all the water would move away. It doesn't do that. The water just oscillates up and down. Okay? And same thing with the ocean. You got waves crashing on the shore all the time. That's only the waves that are coming in. Okay? If it was the actual ocean coming in, eventually the ocean would have a hole in the middle. Okay? And it doesn't ever have that. The water doesn't move from A to B. It just oscillates up and down. Now, that sometimes gives people a little bit of confusion because they've sat on the shore of an ocean or a lake and they've watched the water go in and out. Okay? And they say, Coderre, you're wrong. I know because I've watched this happen. I've watched water come into the beach and then go back out. I know water doesn't just move up and down. Why am I still right in saying water doesn't move in and out? It just goes up and down.
Because it's the energy that moves. Like
It's just pushing it up and down.
Yeah, it's kind of pushing it up and down. It's kind of the energy. It's kind of both of those things. The water gets disturbed up and down. When a wave gets to the end of the water, it's disturbed upwards. Now, there's suddenly no more water for the wave to propagate in. So it leaves the water and enters air. What happens now to the water? It falls. So what you're seeing is the splash of that last disturbance. There's now no energy to hold the water up. So it falls down and splashes inwards and comes back out. Okay? Like people get this idea of like a tidal wave is like the ocean swallowing up, like the whole wave just comes over. That's actually not what happens in a tidal wave. Okay? In a tidal wave, the ocean is disturbed upwards an incredibly large amount. And then when the wave leaves the ocean, all that water, that big column of disturbed water crashes down, and what you see is the splash that's inundating the land that's next to the ocean. Okay? It looks like the ocean is just coming in, and you very rarely see like a big curling wave with a tidal wave. You really just see the water coming in. Okay? It's kind of weird. If you've ever seen like some of the like science fiction movies where a comet hits the ocean and the big wave comes in and destroys everything, it's actually not that bad of a representation most of the time. But in front of that wave, you see the wall of water, and then if they do a good job of the CG, you see all the stuff and people and whatever fly off because of a big shock wave. Okay? That's the wave energy leaving the water and entering the air. That shock wave now travels through the air. Next, so I think I've got the video here.
And also, wouldn't the sand kind of have water in it, so like, wouldn't the water in the sand also rise up a little bit as well?
Well, the sand gets disturbed by the water, but like we're not really considering the waves in the sand. They don't like, yeah, there's some disruption in the sand, but we're mostly just looking at the water itself.
So I
Yeah?
was about to say, like, water can squeeze past, like, in the sand, can be stored in the sand, and then eventually just.
Well, it doesn't store it. Like the
Well,
water, it's
It
saturated.
kind of stays in there, yeah. Before you play, you
I might want to what?
stop recording.
This is my video.
Oh, okay.
But thank you. It's my video. That's me. That's my shadow. The video camera. Okay. All right. So, I mean, we've all seen waves do this, but as they come in, right? So you see, every few waves, you get one that comes in further, right?
Right there where the depth changes, all the waves trip right there. That's where they get big. Right? Like they're very small coming in, you hardly see them, and then they hit that and they rear up and curl. Yeah.
Okay, so I'm explaining it to my son there. But so out here, you hardly see any waves, right? Like there's almost no evidence of a wave, and then suddenly right here where the depth changes and it gets shallow, suddenly it curls over. Okay? And the reason for that is when you're coming in and the depth changes, changing the depth actually changes the speed at which the wave can travel, and it slows it down. But the front of the wave hits that before the back of the wave. So the front of the wave slows down, the back of the wave catches up, and the only place for the wave to go is up. Okay? You don't even really see a tidal wave in the deep ocean. Okay? If you were out on the deep ocean on a boat and there was an earthquake, okay, and a tidal wave started heading for shore, if you were out in the very deep part of the ocean, your boat would go. And that'd be it. Okay? But when that wave gets to shore, and the front of it slows down and the back of it catches up, it's a lot of wave energy. Okay? And all of a sudden it's just gonna pop out of the water like it's, like it's a monster, and there it is somewhere. Okay? So that's kind of what's happening here, okay? But we can see that, yeah, every once in a while that wave rushes in further, but it's only because it got tripped up, reared up, and then the energy left and fell down and splashed in. Okay? And it's a kind of a cycle of waves. About every 3-4 waves, you actually see that happen. So this is, I think, what you were talking about too. You can kind of see it. You can see the cycle there, right? Here's where the depth changes. And if you watch some of the little particles, they kind of do this in the water. They kind of go in a circular oscillation. All right, is that making some sense? Okay, so it's not the wave, it's the wave that's traveling from one place to another, not the material through which the wave is traveling. Okay, that just oscillates up and down. Okay, another good example. Okay, there's a spring. All right. Can I get somebody to hold the other end of that for me? If you can't see the spring, we're going to put it on the floor. Okay? If you can't see the spring, come up where you can see it. Okay? But if I make a wave in this spring, okay, like only the wave travels, right? The spring doesn't jump out of my hand and go towards Jonah. Okay? Just the wave does. Okay? And when it hits Jonah, what happens to it?
Comes back.
Yeah, it reflects. Okay, just like light reflects off a mirror, okay, light's a wave, so it just reflects off of it, okay. Jonah's a reflective surface for this wave, okay. I make that wave, it travels towards him, okay. Am I all right with that idea? Okay, now, right now, those waves are traveling a little bit fast, okay, not super fast. What if me and Jonah both back up another meter or so. What will happen to the speed of the waves now? They'll increase. Why? What did I change? I changed the tension in the spring. Okay? The speed of a wave is affected by what medium it's traveling in, and to an extent, the properties of that medium. Like those water waves. They were always traveling in water, but as soon as the depth changed, their speed changed because they changed a property of the water. Okay? This is how you tune a guitar or any other string instrument. Okay? You make it sound different by tightening the string, which changes the speed at which the wave travels and thus the frequency of the wave it produces. Okay? That's kind of one of the things that you can do to change the speed and properties of a wave is change the properties of the medium in which it's traveling. Okay? Now, which would travel faster? A big wave or a little wave? They're the same. We just said it's the properties of the medium that controls the speed of the waves. Okay? If I make a big wave and a little wave, it's hard to do in this because they travel fast in this one, but okay? They don't catch each other. Okay? They stay the same distance apart. Okay? Because the medium is what controls the speed of the waves. Okay, Jonah, I'll have you let that go. You can just let it go, it'll go back. Thank you for your help. Okay, so the wave travels through from A to B, but the medium simply oscillates up and down. All I did in that situation was move the medium out to the side and back. Okay, and that's all the medium ever did, was move out to the side and back to equilibrium. Okay. All right, I think I have. Oh, that's for interference. Okay, we'll do that later. Okay, so two basic wave types, transverse waves and longitudinal waves. In a transverse wave, the direction the wave travels is perpendicular or transverse to the direction the medium oscillates. Okay, so this is a transverse wave because the medium oscillates up and down, but the wave travels left to right. Okay, so water waves are transverse waves. Okay, is that making sense? The waves I made in the spring are transverse waves. Okay. Everybody all right with that idea? Yes. Okay, the other kind of waves are longitudinal, okay, and they are a series of compressions and what we call rarefactions. Okay, so they're going to oscillate back and forth, and the wave is going to travel parallel to them, or longitudinally. Okay, so parallel. Everyone with me on that? Okay, so those are the two kinds of waves. So sound waves are longitudinal waves because they're a series of compressions and rarefactions. Ever watched a subwoofer? Right? Subwoofer does this. Move back and forth, back and forth. What it's doing is compressing the air, rarefying the air, compressing the air, rarefying the air. Okay, pushing, pushing, pushing. Okay, that's why you can feel the vibration. If you've got, a few subs in the back of the car, okay, you get like a massage. Okay, because the sound waves are pounding against the back of the seat. Okay, so those compressions hit the back of the seat. Okay, those compressions of air. All right. So, terminology here, okay? Transverse wave is one in which the disturbance is perpendicular to the direction the wave travels, and then we've got similar terminology to simple harmonic motion. The maximum excursion of a particle in the medium from equilibrium is still called the amplitude, okay? Any part of a wave that is above equilibrium is called the crest. Any part of a wave that is below equilibrium is called a trough. Okay? And the length of one complete cycle of a wave is the wavelength, which is going to be measured in meters. Okay? What would we call the amount of time it would take one wavelength to pass you? Period. Yeah. Okay, that would be the period of the wave. Okay, so the time for one wavelength to go by is the time for one cycle of the wave. Okay, now on this diagram, they've identified these 2 points as one wavelength. Is this one wavelength?
Yes.
It is. Okay. What about this? Yes. All of those represent one complete cycle of the wave. Right? What about from here to here? No. How many wavelengths is that? Half. Exactly. Okay. Well, that's good. Most of the time I don't get that answer. Nice. Okay. All right, with a longitudinal wave, okay, you've got a series of compressions and rarefactions, which if I go grab a slinky, I can show you. Anyone singing the Slinky song?
There's just Slinky song.
Yeah. Well, there's a generation gap. I'm not going to sing because nobody wants to hear that. Okay.
No, I think we do want to hear it.
No, you definitely don't, and I'm not recording that, so that's not going to happen. Can I get your help again? Sure. Okay. So, if I want to make a longitudinal wave, okay, I just oscillate the Slinky back and forth. Okay, and you can see where I compress it, right? The compression travels towards Jonah, and if I go back, you can see actually where it's the opposite, compression and rarefaction, okay? But they travel parallel, the waves travel in the same direction as the spring is oscillating. Okay, everybody with me on that? Now, if you recall, when I had that fast spring, I was trying to show you that a little wave and a big wave travel at the same speed. Okay, it's hard. They disappear quickly with a Slinky because there's a lot of friction on the ground. But okay, they stay the same distance apart, right? The amplitude of the wave doesn't affect the speed, just the properties of the medium. Okay, making sense? Okay, thanks, Johnny. Just let it go. It'll come back to me. At some point, you'll probably have some time to play with the Slinky. I mean, do scientific stuff with the Slinky.
You want to hear the Slinky song?
Yeah.
No, that's not going to happen.
I'm like,
Maybe I'll find a video of it because I'm not going to sing it. Okay, so does everyone follow what a longitudinal wave is? Okay, so in a longitudinal wave, there's alternating disturbances of compression and rarefaction that travel parallel. So, okay, this is kind of a freeze frame of what we saw with the Slinky. This would be the area of compression. This would be the area of rarefaction behind it. Okay, and those just travel along. This would be one wavelength, okay, of a longitudinal wave. Okay, like a crest and a trough for a transverse wave. There's no crest and trough for a longitudinal wave. Okay, everybody follow me there? All right, so longitudinal waves tend to travel really well through more dense materials, whereas transverse waves tend to travel better through less dense materials. Okay, so when there's an earthquake, the fastest waves that travel through the Earth's crust are actually the longitudinal ones. The transverse ones that make the Earth do this are the really destructive ones, but they travel a lot slower. All right. Okay, so like we said, both transverse and longitudinal waves are examples of periodic waves or simple harmonic motion. Okay, something moving with simple harmonic motion can create a wave pattern. Okay, so when we're talking about properties of a wave, okay, so as we said here, the length of one cycle is going to be termed the wavelength, and we represent wavelength with this symbol. Okay, it's lambda. It's the Greek letter L. It's a long stick supported by a short stick. Okay, that's all you have to draw. When you actually see lambda for real, it actually is drawn like this with curved ends, but we just draw it like this. Okay, so lambda stands for wavelength, so it's going to be a new symbol that you're going to see a lot. Okay, we still have our amplitudes, the maximum distance from the undisturbed or equilibrium position. The amount of time here, that's going to be the period, and the number of waves per second is going to be the frequency. Right. Okay, so all of those terms, they're going to get cycled around again in this unit and with these with this concept. So, no quiz. Tomorrow. Okay? Because we haven't got into waves and the bottom. Okay? So, we're going to keep going with waves tomorrow, guys.